Hello everyone, welcome to SPSVERSITY. So today I'm here with the last part of the coordination chemistry, which is a very important concept. That's a valence bond theory and the crystal field theory, that's VBT and CFT. Along with that, we are going to see small topics like the stability of the complexes and the metal carbonyls. So please watch the video, and if you really like our videos, press like and subscribe buttons. So in the previous class itself, I gave a small introduction about valence bond theory. This is just like how you studied about different shapes of the molecules in the chemical bonding in the grade 11. Okay, so according to this theory, in the valence bond theory, the central metal ion, I'll go back to the coordination complex of the form MLNX, where M is the central metal atom and the L is the ligand and N is its coordination number. So the metal, generally which is a transition metal, this is going to possess the vacant S, P and the D orbitals for the bond formation along with the ligand, and the bond is a coordination bond where the ligand is going to provide the electrons required for the bond. And what is the number of vacant orbitals provided by the metal? That's equal to its coordination number. And the vacant orbitals of the metal are going to overlap with the filled orbitals of the ligand, and that's how the bond is formed in complexes. And depending on the number of vacant orbitals in the metal and the electron pairs given by the ligand and how they are forming the bond, depending on this, the geometry of the complex is determined. And if the inner d orbitals, for example, if you have the outermost valential configuration as 4s and 4p and you have 3d involvement, then it's called as inner orbital complex. And if there is the involvement of 4d orbitals, then it is called as outer orbital complex. And along with that, if there is any unpaired electron left after the hybridization in the central metal atom or the ion, that leads to the paramagnetic property. If there is no unpaired electron, that leads to the diamagnetic property. So we have a list over here. If it is 4, that means around the central metal atom you can expect 4 ligands. So one is this way of arrangement. This leads to the square planar geometry, or M is equal to 4. This leads to the tetrahedral geometry. That's a tetrahedral and the square planar, where each metal is surrounded by 4 ligands. Then the next thing what we have is M with the 3L, which form the trigonal, and then you have 1L and 1L down here. So this is trigonal bipyramidal. Then the octahedral geometry, where M is here, L, 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 L. So it's a square planar geometry above which there is, above that plane you have one ligand, and below that plane you have one more ligand. This is how the shape of the complex is determined. So let's go for the first complex, nickel tetracarbonyl. What you are supposed to do over here is, atomic number of nickel is cobalt, nickel, copper, zinc. So this should be 28. So the outermost electronic configuration is argon, 3d8, 4s2, and you have to find out the oxidation number of nickel. Since carbonyl is a neutral ligand, nickel carries a 0 charge. That means the outermost electronic configuration remains the same. In D, you have 5 degenerate orbitals, out of which you have 8 electrons over here. 5, 6, 7, 8, and 2 electrons over here. During hybridization, these electrons jump inside. As a result, what you are going to get? 1, 2, 3, 4, 5, and can you see these electrons have jumped over here? So you have 4 ligands coming up. So you need 4 vacant orbitals. So the number of ligands approaching is equal to the number of electrons paired donated, which is equal to the number of vacant orbitals. So this is S, and these are 3p orbitals. These undergo hybridization to give sp3 orbitals, and these orbitals are occupied by the electrons given by the ligands. So here, this is one pair of electron given by the one ligand. So like this, 4 pair of electrons are donated by 4 ligands. This leads to the tetrahedral geometry. And once you write the structure, so the hybridization is sp3 and the geometry is tetrahedral, and you see all the orbitals are occupied by the electrons and you don't have unpaired electron. So the molecule or the complex is considered as diamagnetic. Then the next example which we have is tetracyanidoniculate 2. In this complex, if you see, nickel has 2+ charge. That means the configuration will be just 3D84S0. And cyanide being a strong ligand, always you have to think of these ligands. The cyanide and the carbonyl, all these are considered as strong ligands, and all the halogens are considered as weak ligands, and the ammonia and water, all these ligands are moderate ligands. Depending on the situation, they change into strong and weak. So if you take into consideration of those things, then you have 3D8, that's 1, 2, 3, 4, 5, so 8 electrons over here, and then these are the 8 electrons, and for a 0, there are no electrons. Cyanide being a strong ligand, this compels this electron to pair up. As a result, what do you have? These electrons were already here, and then you have, this is a s orbital, sorry, this is a d orbital, and this is s, and you have 4 ligands coming up. That's 4 cyanide ligands, so there should be 4 boxes free. So that's a d1, and then you have the orbital which is s. I'm changing the ink. Yeah. So this is D, this is S, and this is 4 boxes should be free to accommodate the 4 pairs of electrons given by the ligand. So it is D-sp2 hybridization. If it is D-sp2, then the shape will be square planar. And now these boxes are filled by the electrons given by the ligands. This is how the hybridization is going to take place. Now if you see, there are no unpaired electrons, so the complex appears diamantic. We'll go to the octahedral complexes, where there are 6 ligands around the central metal atom. So you have the cobalt complex over here. Cobalt in the state 3+. First you have to write the atomic number of cobalt, write its electronic configuration. Cobalt is 20, atomic number is 27, so it would be 3d74s2. This is the outermost electronic configuration. Ammonia being a weaker, ammonia is a neutral ligand. As a result, you have a charge on cobalt is 3+, so you remove 3 electrons from here, you get 3d64a0. So now what you are going to do? 1, 2, 4, 5, 6, and 2 over here. Just like this. Now the electrons are going to shift because ammonia is approaching. You consider this is a strong ligand over here. As a result, there is pairing up of electrons. This will jump over here, and this will jump over here. What you are going to get? 1 pair of electron, 2 pair of electron, 3 pairs of electron, and 1. Then you have this kind of geometry, and then you see there are 6 ligands approaching, so you need 6 boxes empty to accommodate the electrons given by those ligands. So it is D2 sp3 hybridization. 2 d orbitals, 1s and 3 p orbitals are involved. Now these orbitals are filled by the electrons given by the ligands. As a result, what type of hybridization you have? D2 sp3. When it is D2 sp3, when the number of ligand is 6, that corresponds to octahedral geometry, and there are no unpaired electrons, so the complex is diamagnetic. And also if you see the inner d orbital, so this is 3d, this is 4s, 4p. 4s and the 4p seems outer shell, and 3d is the inner one, so n-1 orbitals are involved, so this is called as inner orbital complex. And if you consider the next complex, that's the complex of cobalt and fluoride. So here what you see is fluorine, which is a weaker ligand. This can't pair up the electrons. You can see over here, this can't pair up the electrons. So these orbitals are unaffected, and there are 6 ligands which are approaching, COF6. So there should be 6 orbitals to accommodate the electrons given by 6 fluoride. So 1, 2, 3, 4, 5, 6. This is 4d. The next shell would be 4d. So what type of hybridization you expect? S, there are 3 p orbitals and there are 2 d orbitals, so it's sp3d2 hybridization. When the hybridization is sp3d2 or d2sp3, the molecule is going to have, or the complex is going to have the octahedral geometry. And also in this structure, if you see, In this case, you have free electrons. Can you see that? There are unpaired electrons, so the molecule or the complex is paramagnetic. And the next thing which you are going to see is the outer d orbitals are involved in the hybridization. So this is called as outer orbital complex. Now we are going to see the bonding in the metal carbonyls. Actually, metal carbonyls are the complexes which are considered as homoleptic complexes. You know what exactly is meant by homoleptic, right? Where homoleptic refers to the complexes where you only have the one type of ligand, and here the ligands are carbonyls. So what's so special about these ligands? Can you tell me that? If you are watching the videos of SPSVERSITY, keep watching and keep supporting. Okay. Yeah. If you have any questions, you can post over here or down. Yeah. So we are going moving ahead. Bonding in case of metal carbonyls, where you have the metals and the carbonyl as a ligand. Generally, whenever you speak about any ligand, metal is going to have some vacant orbitals. It can be S, P, or D, and the ligand is going to give a pair of electron or the ligand orbitals are going to overlap with the metal orbitals, and the ligand is going to give a pair of electron to the metal. As a result, you will have a bond between that's a coordinate bond between the metal and the ligand. But here what is going to happen is in case of metal carbonyl, you should know how to write the electronic structure of a carbonyl. The atomic number of carbon is 6 and the oxygen is 8. Put together, the number of electron is 14, and you have to write the electronic configuration like sigma 1 is 2, sigma 1 star 1 is 2. This you have studied in the grade 11, the chemical bonding chapter. So the outermost occupied orbitals are sigma. So there are a pair of electrons which are present in sigma, and they are donated to the metal orbitals, just like how the other ligands do. So in the carbonyl ligand, the outermost electron from the filled orbital is going to be donated to the metal, and this is a straight overlapping or the direct overlapping which leads to a sigma bond. And now there are vacant orbitals. The pi star orbitals are present. In case of carbon, pi star orbitals are vacant, which are filled with the electrons given by the metal. So this is the sideways overlapping leading to a sigma pi bond. So the ligand and the metal are bonded through two bonds. One is a direct bonding, the other one is a back bonding. So there are two bonds over here, because of which this bond, the metal carbonyl coordinate bond, seems to be very highly stable, and this effect is called a synergic effect, working together towards the same goal. This is about the metal carbonyls. Then we have the next theory as crystal field theory. If you consider the valence bond theory, there were certain drawbacks when you speak about that theory. It didn't say anything about it does distinguish between the strong and weak ligands, just for our convenience, because we know the next topic, that's the strength of the ligands. We have considered them as strong and weak ligands, but generally the valence bond theory doesn't take into consideration of strong and weak ligands. That's the one thing. And the second thing, it didn't say anything about the stability of the complexes. Okay. And it didn't give any explanation regarding the color of the complexes. So to overcome this, the next theory was proposed, that's called as crystal field theory, and CFT. CFT stands for crystal field theory. So according to the crystal field theory, here it's just like it considers the coordinate bond between the metal and the ligand as ionic bond, where the negatively charged ligands and the polar neutral or the polar neutral molecules. So here the ligands are considered as either negative or neutral, but they should be polar. They should be polar molecules which form the same type of ionic bond with the metal. Okay, so all the d orbitals which are present, all the 5 degenerate d orbitals present in the metal are degenerate. That's what it considers. And when the ligands approach, the orbitals are no more degenerate, but they get split. This splitting is called as crystal field splitting. And what type of ligand is approaching, depending on that, the orbitals are going to split. In simple terms, metal is going to have, since it's a transition metal, it is going to have a set of 5 degenerate d orbitals, and those degenerate d orbitals are going to split in the presence of ligands, and how much they are going to split, that depends on the strength of the ligand, and this is called as crystal field splitting. And when we consider this is what we have to consider. When we consider the shape of the d orbitals, we know that the d orbitals have there are 5 degenerate orbitals, namely dxy, dyz, dzx, dxz, and wait a minute, dxy, dyz, dzx, and dx square minus y square, and dz square. These are the 5 degenerate d orbitals. And if you see these orbitals, can you see these orbitals? What's the difference you can see? Here, in the first 3, dxy, this one, sorry, yeah, in this one, dxy, dyz, and dzx, these form a set of orbitals where their lobes, lobe in the sense this part, this is a lobe, lobes lie in between the axes. And this is dx square minus y square, and this is dz square. If you see, their lobes lie along the axis. Now, in the absence of any ligand or the neutral polar molecule, these orbitals of metal are degenerate when they approach. Depending on what direction the ligand is going to approach, their degeneracy is going to change. So now the d orbitals are going to split. This is how the octahedral molecule is. If you see the structure, the inner one which is present over here, can you see that? This is a central metal atom or central metal ion. And if you see the red balls over here, these are considered as ligands. All of these are ligands. And when you consider these ligands, so when you consider these ligands, what direction are they approaching? Can you tell me that? Are they approaching along the axis or in between the axis? I just want you to answer these questions. If you're watching this, so here the direction of approach of ligand, is it along the axis or in between the axis? You can see these are the xyz, this is x, this is y, this is z axis. If you consider, the ligands are present along those axes. So in case of octahedral complexes, the ligands approach along the axis. So the direction of ligands which are present and the approach of the ligands is along the same direction. As a result, see, this is the in the diagram, the degenerate orbitals of free metal ion. If you consider the free metal atom, all the orbitals are degenerate, and when all the ligands come from equidistance, they are approaching, they are coming from equal distance, so they are, because of the electrons of the free metal ion and the electrons of the ligand, there is a repulsion. As a result, due to the repulsion, the energy of these orbitals is going to be little higher. That's why from here they have stepped into a next step. And when now the ligands are approaching along the axis, so there is, along the axis there is more repulsion. You can see that. So ligands approach along the axis. When they approach along the axis, whatever the orbitals which are present along the axis, that's dx square minus y square and dz square. the energy of these orbitals is going to rise. Whereas the energy of the other three, which are in between the axis, what are those? dxy, dyz, and dzx. Their energy is going to go down. So you can see that, and the difference in the energy between these two orbitals or these two sets, that's the lower set is called as T2G and the higher set is called as EG. The energy difference between these two sets is called as delta O, stands for crystal field splitting energy, that's delta, or it is also called as CFSE. O stands for octahedral over here. It's not the 0, is octahedral. And if the energy difference between these two is called as 10 dq, then the energy of these two orbitals are increased or raised from 0 level by 0.6, and the energy of the lower orbital is going to decrease by 0.4 crystal field splitting energy. This is how the splitting is going to happen in case of the octahedral complexes. So now we have the topic over here that's called a spectrochemical series. So this crystal field splitting here, okay, if you see in the previous image, they are split, right, over here. This splitting, how much should be the energy gap between these two sets, that's decided by the ligand, what type of ligand it is. So if you have a list of ligands and if they are arranged in the increasing order of their ability to cause the splitting, so you have the d orbitals and they should split, and how much should the d orbitals are going to split, that depends on the strength of the ligand. So if you see, the halogens come in the beginning, and then you have water, oxalate, ammonia, ethane 1,2-diamine, NO3 minus, NO3 minus, Cn minus, and at the end you have carbonyl as a ligand. So this is how their energy is going to increase. Okay, so the one which are found at the right side, that they have more energy to split the orbitals, whereas the groups or the molecules which are found in the beginning of the spectrochemical series, they have less impact on splitting. That means they can't split the degenerate orbitals into two sets with a greater height. Okay, so the ligands on the left, that's halogens, they cause small crystal field splitting and considered as weak field ligands. Yeah, so these cause the halogens, they cause smaller crystal field splitting and they are considered as weak field ligands. What do you mean by weak field ligands? Since they split the degenerate orbitals into two sets with the less energy in between, then they can't cause much splitting, so they are weak field ligands. And also these form high spin complexes. These can't pair up the electrons in a given set, so these form high spin complexes. That means you have more single spins, whereas which are found on the right hand side, extreme right of the spectrochemical series, they are strong ligands and they cause greater splitting. And once this greater splitting is caused, and they have the energy to pair up the unpaired electrons. So these are called as strong field ligands, and when the electrons are paired up, you get low spin complex. Okay, so okay, let me go to the previous slide. Here, if you have T2G set and EG set, and you have D1 configuration, the first electron goes here. If you have D2 configuration, the electron is going to go over here. If you have the third one, So, sorry for the technical glitch. I'm continuing from here. And yeah, if it is a D1 configuration, one electron is going to go over here. If it is a D2 configuration, the second electron is going to go here. And if it is a D3 configuration, the third electron enters here. And when it is D4 configuration, if you have the D4 system, what you have over here is 1, 2, 3. The fourth electron has two choices. The fourth electron can go over here, or the fourth electron can go over here. So you have two choices. One is pairing over here, and the second one is jumping to the EG set. So if it pairs over here, that's if the pairing is going to happen, then what configuration you get? T2G4 EG0. If it's the jumping to the next level, that's no pairing, then what configuration you have? T2G3, 3 electrons, and EG1. Now, according to this, how do you decide whether the electron is going to stay there only or it is going to go? So there comes the weak and the strong field ligands. If it is a strong field ligand, the splitting is greater. That's a delta. You have two factors over here. One is this splitting. This is crystal field splitting over here, and this is also crystal field splitting over here. And then after this, what you have here is the pairing energy. You have to consider into these two factors. If the gap is wider, this one, then the electron can't jump from here to here. That means I'll take pairing energy. The energy gap is higher. That's a crystal field splitting is higher than the pairing energy. So pairing is lower. So the electron is going to choose the path of lower energy. The electrons are going to pair up. That's the case which happens here, pairing. When the pairing energy is lower, the electrons are going to pair up. When the crystal field splitting energy is lower, the electrons are going to go to the next level. That depends on what type of ligand is approaching, which causes the splitting, and that decides the spin of the complex, either the low spin or the high spin. So we have different examples over here. You can see that if crystal field splitting energy is greater than pairing energy, pairing occurs. If the crystal field splitting energy is lesser than pairing energy, no pairing is going to happen. So you have different examples. Here in the example UE, what is written over here, that stands for unpaired electrons. 1 UE, 1 unpaired electron, 5 UE, 5 unpaired electron, 0 UE, 0 unpaired electron, 4 unpaired electrons. This is what you have to remember in each and every case. And here the splitting energy is higher. You can see that crystal field splitting energy is higher. As a result, the electrons, because the crystal field splitting energy is higher, the electrons are going to jump. No, they are not going to jump. Instead of that, they are going to pair. Okay, and if it is 5 unpaired electrons, what do you mean by 1 unpaired electron and 5 unpaired electron? That depends on the crystal field splitting. So if the crystal field splitting is more, so the electrons can't choose this, go to the higher level. So they pair up over here, here. So there is only 1 unpaired electron. If it is a D5 system, and if the pairing energy is more and the crystal field splitting energy, this energy is less, the electrons are going to stay over here. Okay, and if it is a D6 system, if the splitting is more, which is caused by the strong ligands, electrons are going to pair up. If it is a weak ligand, it can't pair, cause greater splitting, so the electrons are going to go to next level. Less pairing, 1, 2, 3, 4, 5. Once all these degenerate d orbitals or the split d orbitals are going to be occupied by the single electrons, then the pairing is going to happen. You see 4 unpaired electrons in this case. And if it is a D7 system, first if the splitting is greater, 6 electrons are going to be filled in the lower sets, then the 7th one, which has no place down, that's going to go to the top. If it's D7 system and you have a weak ligand that can't cause greater splitting, the electrons are filled up lower in the lower orbitals first, followed by the next orbitals. So how do you calculate the crystal field splitting energy? Any electron which enters to the T2G level, that should be multiplied by minus 0.4 because the energy of those orbitals are lower, and any electron which is going to go to higher level, though that should be multiplied by 0.6. That's any electron present in the EG set. This is how you find out. For example, if this is the case, how are you going to calculate the crystal field splitting energy? Crystal field splitting energy is equal to the electrons are, all the 5 electrons are present in the lower level. This is how we are going to calculate. The crystal field splitting in case of tetrahedral complex. If you consider the tetrahedral complexes, here the ligands are approaching in between the axes. You can say that. This is the XYZ axis as shown in the first diagram over here. In this diagram, if you consider the complex, the ligands are approaching in between the axes. X, Y, Z axes are over here and ligands are in between. Can you see that? So the DXY, DYZ and DZX, which have their lobes in between the axis, their energy is going to increase, and dx square minus y square and dz square, these orbitals have their lobes along the axis, their energy is going to decrease. And you see the reverse type of splitting. So you can represent them in this way also, just like previously you represented 5 orbitals like this or 5 boxes like this. You can represent them in any way. So when the ligands are approaching equidistant from same distance, their energy, the energy of the orbital is going to rise due to electronic repulsions. And when the ligands are approaching in between the axis, you have EG set where the lobes are along the axis, and these sets where the lobes are present in between the axis. So this forms E and T rather than EG and T2G, which is represented in case of octahedral complex. In case of tetrahedral complex, you are going to write E and T. And the energy is called as delta T. That's a crystal field splitting energy. In case of T stands for tetrahedral complexes. And the energy of these two orbitals is lower by 0.6, and the energy of this orbitals is increased by 0.4. And just like the previous case, you are going to fill the electrons. But in case of tetrahedral complexes, the tetrahedral splitting energy is considered as much lower than the octahedral splitting for the same type of ligand. So delta, that's a crystal field splitting energy for the tetrahedral complex, is half, more than you can say it's almost 40% what is observed in case of octahedral complexes. Then we are going to see the color of the complexes. Most of the coordination complexes are colored, because when you pass the visible light, the visible light consists of 7 colors, you know that. And when white light is passed through the sample, you have the visible spectrum, and some of the components are absorbed by that complex, and the complementary color is observed. So it depends on what type of wavelength is absorbed or what type of color is absorbed by the complex. If the complex absorbs green color, it is going to be appear as red. For example, you have that color chart where you are going to take Vingior and you are going to plot the circle, and you find which is a complementary color. Why the coordination complexes are colored? Because in case of coordination complexes, you have 2 sets. One is the T2G, other one is the EG. Now, the electrons are transferred from lower level to the higher level when the complex is going to absorb some radiation, and when that electron comes back to the original state, That's going to give the light. So the major reason for this is DD transition. Electrons are transferred between lower D set to the higher DD set. That's called as DD transition. And there are some conditions, like if all the electrons are paired up, you don't have unpaired electron for the shift. In that case, you don't see the color for the complex. And there should be vacant space in the higher D set, otherwise the electron from the lower set can't go to the higher set and there is no color observed. Okay, this is the reason for color of the complex. For example, what is it called? Ti3 plus ex-aqua titanium, scandium titanium. The atomic number is 22, so this is 3d to 4s2. When it is 3d titanium 3 plus, the configuration is 3d1. So there is one electron in the lower set which is going to jump to the higher set. That's why it has some color. Now if you remove the ligand, you have just Ti that is not going to show any color. So the presence of ligand is a must, because that is the one which is going to cause the DD splitting. If there is no ligand, no DD splitting, no transfer of electron, no color. Now we are going to see the stability of the coordination complexes. So what do you mean by stability? In case of coordination complex, you have what exactly is meant by the stability of the coordination complexes. Whenever you say stability, there are two types of stabilities. One is a thermodynamic stability, the other one is the kinetic stability. How strong the bond, the coordination bond is between the metal and the ligand, that leads to that's what is referred as stability. Okay, I'm just looking, so no one is watching as of now. So when you're going to watch this video, I wish you like our videos and subscribe. There are good teachers who are part of SPSVERSITY. So keep watching the videos and keep supporting. That helps us a lot. Okay, and if you have any comments, you can post it in the chat box, or if you are looking at this videos, like if you are in the live session, you can even live chat. Yes. So moving ahead. Whenever you see the complexes, when you put them in the aqueous solution, they are going to split into the complex part and the counter-ion part. That's called as primary dissociation. And then again, if the complex is not so strong, this can further dissociate into the metal and the corresponding ligand. If it doesn't dissociate, then it's called as a stable complex. If it is going to dissociate, then it is not so stable complex. So this is called as the secondary dissociation. So we have something called as stability constant, which is called as beta. Okay, what do you mean by this stability? So if you have to replace the existing ligand which is present in the complex by some other ligand, then that particular ligand which is already existing, that should be dissociated. That's again stability. So the stability of the coordination complex, it is a measure of how hard it is to replace the existing ligand by the other. Okay, so there should be the association between the central metal atom and the ligand. So the bond should be sufficiently strong, so the complex doesn't undergo dissociation easily. So you have a complex formed, that's a Cu2 plus combines with 4 ammonia molecules to give the complex CuNH3 4 times 2 plus. And how, since they are in the equilibrium, how are you going to write the beta? That's the stability constant. Concentration of the product divided by concentration of the reactants. Cu2 plus NH3 to the power 4. These stoichiometric coefficients become the power. And so if this is greater, then beta is higher. So if the stability constant has to be higher, then product should predominate. That means the complex should be more stable. So the same reaction can be represented in different ways. For example, Cu can combine with 1 NH3 in first step, and the CuNH3 complex That's 2 plus complex can combine with one more NH3, and in the next step Cu NH3 twice. 2 plus can combine with one more NH3, and like that, and this Cu NH3 for 3 times 2 plus, and it can combine with one more NH3, and all these are called as, and you're going to find out K1, K2, K3, K4 over here. How are you going to write K1? Thus the complex CuNH3 in the first case 2 plus NH3 1 times over concentration of Cu 2 plus times NH3. And the second one, I'm going to erase the mess I have created. What's K2 over here? K2 is equal to CuNH3 twice 2 plus divided by CuNH3, that's the reactant, plus times NH3. And K3 is equal to CuNH3 2 plus divided by CuNH3 twice 2 plus times NH3. Then the K4, that would be equal to CuNH3 2 plus divided by CuNH3 thrice 2 plus times NH3. When you multiply all these, that's K1 times K2 times K3 times K4, which is equal to, all this get cancelled. You can see that CuNH3 gets cancelled, and CuNH3 gets cancelled, NH3 gets cancelled. So what are you left with at the end? You are left with CuNH3 4 times 2 plus over Cu 2 plus times NH3 4. So that's nothing but beta. So this beta is called as overall stability constant, and this K1, K2, K3, K4 is called as stepwise stability constants. So moving on to the MCQ section. From the stability constant, that's a hypothetical values they have given, predict which is the strongest, you have to predict which is the strongest ligand. Can you please predict which is the, I'm waiting for your answers if you're watching. So what is K over here? This is stability constant. Higher is the stability constant. Greater will be the stability. So if you see the K value seems greater for this one. So higher the value, higher will be the stability of the complex. So less will be the dissociation. So the correct answer will be option B. High spin D4 octahedral complex they have asked. Crystal field stabilization energy for high spin D4 octahedral complex. What you can say about this? What do you think the answer is? Yeah, let me proceed with the answers. They have mentioned it as high spin. And the configuration is D4. How are you going to do that? So you have a set of degenerate orbitals, that's D. And if you have D4 system, there should be 4 electrons. And after splitting, octahedral they have mentioned. This will be this type of splitting. This is T2G, this is EG. So this is DXY, DYZ. and D ZX. So high spin, so 1, 2, 3, high spin in the sense the electron should go to the next level, and any electron which is coming to this level, that is given with the sign, the number minus 0.4, and any electron which goes to the EG level, that is assigned with the value of 0.6. So how do you calculate the crystal field splitting energy? Crystal field splitting energy is equal to minus 0.4 times the number of electrons in D2G, that's 3, plus 0.6 into 1. The correct answer would be option. We'll go to the next one. The correct statement among the following is COCN6 3 minus is. It has no unpaired electron and will be a low spin configuration. It has 4 unpaired electrons and will be in a low spin configuration. It has 4 unpaired electrons and will have configuration, and it has no unpaired electrons and will be a high spin configuration. Now you have to find the correct answer for this. What is your answer? Okay, let me proceed how to answer this. If you are watching, you can quickly answer. You can try your luck too. So CO is in the 3 plus oxidation state over here. If CO is cobalt, nickel, copper, zinc, so the configuration is 3d7, 3d7, 4s2. If you remove 3 outermost electrons, it will be 3d6, 4s0. So you have 1, 2, 3, 4, 5, 6 electrons over here, and 4s is empty, 4p is also empty. When the ligand is going to approach, cyanide is called as strong ligand. So these electrons are going to pair up 1, 2, 3, 4, 5, 6. And what type of hybridization you have? D2sp3. And you don't have any unpaired electrons, so select the one with the no unpaired electron, option 1 and 4. And it is a low spin configuration. So when you have the strong ligand, when the ligand is strong, that causes greater splitting. So CFSC is high. So electron can't jump to the higher energy level. Instead, it chooses to pair up. So no unpaired electrons, and it should be a low spin configuration. That would be the correct answer. The complex showing a spin only magnetic moment of 2.82 GeM is. What is the answer? What could be the answer according to you? So we know that spin only magnetic moment is equal to root of n into n plus 2 Bohr magneton. N, where n is the number of unpaired electrons. You have to see the number of unpaired electrons. Nickel, what's the number of unpaired electrons? So carbonyl nickel is a 3d8 4s2. The electrons pair up. So the number of unpaired electron is equal to 0. Here nickel is in the 2 plus oxidation state, 3d8, and here there can be unpaired electron, but here and here you don't expect any unpaired. Wait a minute. Here also the n is equal to 0, and nickel 2 plus 3d8, and again the cyanide is a. Let's write the configuration to avoid the confusion. Nickel is in the 2 plus oxidation state, so 3d8 for a 0, and cyanide being a strong ligand, this is going to pair up the electron. So here also you don't see unpaired electron. So the unpaired electrons are present only over here. That's nickel is in 2 plus configuration. That's 3d8, So 1, 2, 3, 4, 5, 6, 7, 8. You have 2 unpaired electrons. N is equal to 2. So root of 2 times 2 plus 2, that's 8. So the correct answer will be option B. Atomic number of chromium and the iron are respectively 24 and 26. Which of the following is paramagnetic with spin of the electron? What will be the correct answer? So first complex, here the oxidation number is equal to 0. The number of unpaired electrons is equal to 0. Here also the oxidation number of the metal is equal to 0. So the question is, which of the following is paramagnetic? So if it is chromium and carbon is a neutral ligand, here the electrons are going to pair up. So if it's 3d5 4s1, 1, 2, 3, 4, 5 and 1, during the jumping this will shift over here, this will shift over here, and other electron will shift over here. So here no spin, no free spin available. Fe, that's 3d6, 1, 2, 3, 4, 5, 6, and this will jump here. So this will jump here, this will jump here, and the next 2 electrons are also going to jump. No free spin. Then FeCN 6,4 minus. Here Fe is having 2 plus charge, so the configuration will be 3d6. When it is 3d6 again, this ligand is stronger, so no free spin, no unpaired electron. We are left with the last one, Cr3 plus NH3 6 times 3 plus. The configuration is 3 plus. That means chromium is in the 3 plus state. So if you remove 3 electrons, 1 will go from here. You have 3d3. Whatever may be the type of ligand, it is odd in number. As a result, the correct answer would be the last one, option D. Which of the following complex has the square planar shape? That's d-sp2 hybridization. When it is square planar shape, it is understood that the complex is going to have d-sp2 hybridization. All of this. We'll start with the first one. Nickel tetracyanide-nickelate 2 complex, and nickel will be in 2 plus state, but it is a strong ligand. Cyanide is a strong ligand, so it is going to pair up the electrons. So 3d8 configuration it is going to have when the 2, 3, 4, 5, 6, 7, 8. Again, this is going to pair up. So this you can expect this sp2 hybridization over here. And the next one is CuNH3 4 times 2 plus, and the PT Cl4 2 minus. So what do you think about these complexes? If you are watching this, you can please put a comment over here, like which is the correct answer. So if you take copper complex, that is in the 3D, copper is in the CO2 plus state, right? CO2 plus state. When it is CO2 plus state, you generally 3D10 4s1 will be the configuration. It is 2 plus state, that means 3D9. Again, there is one odd electron over here, so this can't have the dsp2 hybridization. So either all of this, but this is not dsp2. So the correct answer should be option A. That would be the right answer. Among the complexes, the hybridization states of nickel atom, it's easy to determine actually. Nickel is in the 0 oxidation state, so the NiCO4, nickel is in the 0 oxidation state, 3D8 4s0 4s2. So all electrons are going to pair up. So this will be sp3. So you have A, B, C as the option. We'll go to the second one. Nickel tetracyanide 2 minus. So the configuration would be 3d8. The electrons are going to pair up. And what type of hybridization you are going to have over here? If it is dsp2. So the correct answer should be either A or B. And the last one, nickel tetrachloronickelate. Here the configuration would be 3d8. And the electrons are not going to pair up. So the configuration, because chlorine is a weak ligand, as a result, the correct answer would be option B. So thank you so much for watching. Keep supporting.